I don't know. All right. That was that.
Do they want to see the video?
So the title is Large-Scale Groundwater Discharge Modeling Supported by Innovative Hydrogeological Characterization. And here is my presentation outline. I'll give you some general background of the study first, and then to the details of the aims and methodologies that I'm going to follow in each chapter, then my future plan at the end. So to start with, as a general background, I think it's important to define submarine groundwater discharge. And I want to remind you that I'm going to use SGD as an abbreviated form of submarine groundwater discharge in the next slides, rest of the slides I would say. So when there is an aquifer discharging water to a marine system or to the ocean through the bed of the ocean, that kind of discharge is known as submarine groundwater discharge. And the widely used definition of SGD is it's any flow of water at continental margins from the seabed to the coastal ocean regardless of fluid composition and driving force. Here I have a video. Of course, SGD has different exits, it follows different pathways to exit through the bed of the ocean. And I have a video here that shows one of the exits, the pathways that SGD could follow. This is actually a simple example of it, how SGD exits through the bed of the ocean, and it's at the shoreline. And as far as this SGD is concerned, it has been recorded since the early times. And one best example of this is the report made by the Roman geographer Strabo. It was reported in 1580. He revealed the existence of submarine groundwater discharge or submarine spring in the Mediterranean Sea in 1580. So this tells us that SGD was recognized in the early times, but it was ignored from the research agenda until the 19th century. But since then, it was recognized in two ends. One end is that SGD could be an alternative freshwater resource for the coastal community to balance the water supply demand. And the other end is SGD could be a pathway for contaminant transport in the coastal area. And different forces could drive SGD, but the forces could be grouped into two, actually main groups. One is the inland origin, and the other is the marine origin forces. Example of the terrestrial or inland origin force is the hydraulic gradient. When there is a gradient, head difference in water, that head difference creates pressure for water to flow, for groundwater actually to flow through the bed of the ocean. And here, the different pathways that I said earlier on, that SGD could follow different pathways to flow through the bed of the ocean. One is when it comes due to the force, the inland origin forces as a fresh groundwater in the offshore, and it can also be recirculated due to the ocean origin forces, and it's just recirculated SGD. These SGD components could just appear at the shoreline, and they are called onshore discharge. And the other pathway that SGD could follow is the fractures or the fissures through the confining layers. Here we'll discuss actually the different types of aquifers later, but this one is unconfined aquifer above this confining layer. Unconfined means it's just open to the atmosphere, means it just directly gets recharged from the precipitation. And there is a confining layer here, and if the confining layer has fractures or fissures, then the groundwater could follow that fissure, that geological discontinuity, and that type of discharge is called offshore discharge. Or sometimes it could also follow the end, or it could just exit through the end of the confining layer, and that is called submarine spring. So these are the different exit points, different pathways that SGD could follow, and the different components of SGD. And this shows us that the different aquifer types, or the geologic and hydrogeologic setups of the aquifer system, control groundwater flow. That's the aquifer system. The setup of the aquifer controls the flow of groundwater within the different types of aquifers. By definition, aquifer is a geologic formation. It's a permeable geologic formation that could store and conduct water. I have here two examples of aquifers. This is the unconfined, a representative block of the unconfined aquifer, as you have seen it earlier on. This has no confining layer at the top. This one is a virus zone, unsaturated zone, and here we have the water table, and this is the saturated one. No confining layer at the top, and this type of aquifer is unconfined. The other is confined, which has confining layers from the top and bottom. And if this confining layer at the top is leaky, that type of aquifer is called semi-confined or leaky type of aquifer. But we can have also purged, which is fake aquifer. So the main thing here is the setup of the aquifer system, the nature of the aquifer system, the connectivity of the pore spaces within the different types of aquifers controls the flow of water within the aquifer system. Now, it's really interesting to know that understanding the setup of the aquifer system is a basic input for estimating SGD. Now, it's not only understanding the aquifer system, understanding the different methods and the uncertainties associated with the different methods is also important. We have different methods of SGD estimation. Here I have different examples. This is the piezometer method, which is based on the head differences of water within the aquifer system, the natural tracers, seepage, and some others as well. We will discuss them later on. But what we have to highlight here is none of the methods developed so far considers the varying components that we have seen earlier on of SGD. That means they have their own limitations in estimating SGD. So understanding the basic differences, that is the strengths and limitations of each method, is very important before estimating SGD using any of the methods developed so far. Here I have some examples. Actually, the widely used methods of SGD estimation in here, in the left side, and the different criteria that I use to classify the methods from the literature. The nearshore and offshore consideration, the fresh and recirculated SGD separation. We've seen how it circulates and how it appears at the shoreline as fresh, or their application at different scales. Now, some of the methods are only applicable at nearshore, in the nearshore discharge, and some of them are applicable, or they just consider both the fresh, the nearshore and the offshore SGD components. And some of the methods only estimate the fresh component, while some of them estimate the recirculated only, and most of them give us the bulk estimation of SGD. And some of them are applicable at local, some of them are applicable in both local and large scale. Here we can understand that they have differences, so they have their own limitations as well. And that's why the comparison is very important in the first instance. Now, one of the methods that could be applicable at local and large scale is the numerical modeling, which is actually the widely used numerical model is mudflow. It was applied in the Gulf of Mexico by Kevin Buffett. He's one of my supervisors. Actually, that's a good input for this work. He applied it. Actually, they applied it with his friends. They applied it along the coastline of the Gulf of Mexico, and they found interesting results from there. And we think that this could be applicable in our area as well. We'll discuss it later. Now, what should come to our mind when we discuss about SGD is the nutrients or the contaminants it could drive with it. Different problems are just getting discovered in different parts of the world due to the nutrient enrichment in coastal areas. Nutrients could affect the biogeochemical budgets of the coastal areas and causing different problems like different biodiversities are dying, eutrophication problems. As you can see from this figure, different areas are just being affected by eutrophication, the yellow highlighted ones, and different areas by hypoxic problems like the red highlighted ones. And hopefully, some areas are under recovery. So SGD may be one of the important pathways that nutrient could follow in the nutrient enrichments in coastal areas, even though it was ignored in the previous studies. But recently, we have studies, some experts have revealed that the nutrient driven by SGD are even more important than nutrients driven by river discharge. Liu and others in Bohai Sea, China, reported importantly that even though the water discharge from river is greater than the water discharge from fresh SGD, the dissolved inorganic nitrogen from fresh SGD is greater than the nutrients that could be driven by rivers. That's very, very important highlight. Here, another study which was conducted at global scale showed us that the dissolved inorganic nitrogen, phosphorus, and silicon that could be driven by SGD are 1.4, 1.6, and 0.7 folds higher than the river discharge. And this is also another important highlight. Now the question should be, how about in the Great Barrier Reef? How about in the Great Barrier Reef? My study area is Great Barrier Reef. And as you know, Great Barrier Reef is a World Heritage Site since 1981, and it's the largest reef system in the world. It attracts around 2 million visitors per year, and the biodiversity is really extraordinary, as you can see. This is a very simple example of it, and it's contributing hugely to the economy and environment of the country, providing around 64 full-time jobs. But this extraordinary reef system is facing different problems. Reports are showing that the reef system had lost half of its coral cover from 1985 to 2012. And different causes are associated to here. Bleaching is one, and the coral-eating starfish is another, and eutrophication is also one. In our case, eutrophication is affecting it really hugely. And the main cause of eutrophication from the previous research is implicated to be decrease in water quality, while the cause for the decrease in water quality was reported to be the nutrient loss from agricultural farms. And the question here as well should also be, what has been done from the government and researchers' side? The government have been engaged there, they've been involved, including the recently announced fund, which is around $500 million to tackle the pollution in the Great Barrier Reef and to breed resilient corals in the Great Barrier Reef. And different studies have also revealed different sources, as you can see it from here, different sources of the nutrients in the Great Barrier Reef. Benthic release, runoff, and switch, and others. But what you can realize from here is the only accounted part of the sources of nutrients in the Great Barrier Reef is around 30%. The remaining 70% is unaccounted. And what we can use as a highlight is the majority of the studies in the area are concentrated on river discharge. And that shows us the role that SGD plays in terms of enriching nutrients in the Great Barrier Reef is uninvestigated. And that is a gap that we are going to fill. Because understanding how and when nutrients enter the sea aquifer system and discharges to the marine system is very important. So to do this, to fill the gap, we conceptualized here the coastal aquifer system, or the hydrologic cycle, and the probable aquifer systems in the coastal area. And the hydrologic cycle, the different activities in different coastal areas are highlighted here. That's the conceptual diagram of the overall study. But we decided to first compare the aquifer characterization methods at small scale and then apply it in the large scale in the whole Great Barrier Reef, just using the selected appropriate aquifer characterization methods. But after this, we also need to compare the methods that could be used to, the appropriate methods based on the literature comparisons and an actual comparison at the field to estimate SGD. There are different methods as we have seen earlier. So methods comparison to identify the uncertainties of the method that we are going to use is very important as well. And then we will apply the one that was applied in the Gulf of Mexico by Kevin Buffett. That's numerical modeling to estimate SGD throughout the whole coastal system in the Great Barrier Reef. And then this will help us estimate, that's upscaling it by the nutrient concentration of the groundwater in the membrane to estimate nutrient in the Great Barrier Reef. So as far as the first chapter is concerned, we selected one watershed in Ethiopia, that's Lake Arefayne watershed, because we had a data for, and we compared three methods of aquifer characterization: the geologic method, hydrogeologic method, and the geophysical method, because these methods are the widely used methods for aquifer characterization. We compared the methods, identified the uncertainties associated with the single method uses, and the aquifer system was characterized using composite method, the composite form of these three methods. Productivity and sustainability of the aquifer system were evaluated. From that, what we found is this. This one is a very important, very interesting representation of the heterogeneous nature of the aquifer system. This is a lithologic map of the aquifer system in the Lake Arefayne watershed, and you can see the different earth materials in here. And then homogenizing these different layers based on the dominant formation within the aquifer system gave us this stratigraphic unit, stratigraphic map model of the aquifer system. And this is very important to first understand the type of aquifer. From here, it's only the highlighted one that we have as a confining layer, the hard pond, the hard formation. That shows us above it are unconsolidated, so the aquifer system is unconfined. It's unconfined. And the thickness can be estimated, the thickness of the potential aquifer actually can be estimated by the water level measurements and the formation nature, and the thickness of the overburden as a whole. And not only that, actually, we compared results of hydraulic properties of the aquifer system from the three methods: the vertical electrical sounding, pumping test, and geology. These are the methods that have been used in estimating aquifer properties. And the geologic method gave us a wide range, while the rest gave us kind of small range. But the most important thing here is the median values of the hydraulic property, hydraulic conductivity of the aquifer system lay at almost the same line. This shows that the methods could be complementing to each other, and one could be used in the absence of the other. And using the results from the geologic characterization, the type of aquifer, the nature of the aquifer, the number of aquifers here, because single aquifer we identified in here, and these values to mudflow, and then we predicted the sustainability of the groundwater in the area. And based on the current use scenario, we found out that the groundwater will reach below pumping position in 26 years. That means the groundwater is being overexploited. So from that comparison, we decided to use composite method of the geologic and hydrogeologic method in the Great Barrier Reef, because we don't need any geophysics. Because of that, we have a really huge number of wells, and then the drill logs could be enough to characterize the aquifer system. So what we are looking to get, what we're expecting from this chapter is just the surface geological map of the area, 3D lithologic and stratigraphic maps, hydraulic properties of the aquifer system, and then at the end, the connectivity, the hydrologic and hydrogeologic connectivities. The hydrogeologic will be actually developed from these drill logs and pumping tests. Now, to do that, we will just use the digital geological map of the state as an input, well construction reports including drill logs and pumping tests, another input, and the water levels. These all are going to be inputs for rock works and aquifer tests. Then we will end up understanding the nature, the type, and number of aquifers, just like these types of maps. That's very detailed cross-sections of, that's the fence diagram of the aquifer system. And then this is stratigraphy. Then the conceptual diagram of the aquifer system will be developed at the end. Thirdly, we will compare the methods these actually selected methods from the methods that could be used to estimate SGD. We'll compare seepage method, piezometer method, natural tracers, and numerical model at a relatively small scale. Actually, the Burden area, it's not small, but relatively small scale. And then it's just because of we have data for some of the methods that we are going to use in the area. So the seepage meter is going to be the automated seepage meter, and we'll deploy that in 50 different stations. At the end, we'll use the Darcy's law and the law of conservation of mass to estimate SGD. And the piezometer method, we will measure water levels. Actually, there are measurements of water levels of the different wells that you have seen from these. And the difference in height is going to be used to estimate the SGD together with the conductivity that is going to be estimated from the pumping test. Darcy's law is the main analytical equation that we are going to use to estimate SGD here. Natural tracers, we will use composite of the radon and radium isotopes. Time series measurements of these isotopes will be taken. And the mass balance of these isotopes will give us an estimate of SGD. And the fourth method that we're going to compare to the numerical model is going to be mud flow. And then by combining these four methods, we will at the end come up with kind of comparison and identify the uncertainties associated with the single method use. And then recommendation at the end, even if the composite use is important or not. As far as the modeling is concerned, the numerical model, as I said earlier, is going to be mud flow. It's going to be mud flow, and we'll run it through Python. The input data for this model are the aquifer type from the characterization, number of aquifers, the thickness of the aquifer, the hydraulic properties of the aquifer system, that's conductivity, transmissivity. All this might be new for you, but it's all about connectivity of the aquifer system. That's how water flows from place to place. And then the water levels, recharge and discharge from the area. The input data will be the extent of the aerial extent of the aquifer will be used to generate the grade and the thickness of the aquifers as well. And then there will be different loops, time and flow, and then we will solve using different solvers, and the convergent flow will be solved. At the end, the result is going to be height. But as you know, the Great Barrier Reef is really huge in area coverage, so we're going to divide it into different model areas to incorporate heterogeneity based on the water divides, geologic similarities, and climate. And we will consider the different boundary conditions. It's all about identifying boundary and using different zone budgets in mud flow to estimate the SGD. And here we have the physical, maybe examples of physical boundaries, rivers, or if there is a mountain in there, or geological formations outcropping areas, that will be considered as a flow boundary, or general head boundary like this, the ocean end is going to be considered as general head boundary. And the elevation model will be used to trim, to clip the model area into the shape of the watershed. Finally, we will use the water levels from the wells as initial and prescribed head. And as I said, the result is going to be head of water, and we will interpret that using Python, but zone budgets will be importantly used because it's all about creating zones in mud flow to estimate SGD from the different aerial extents like this. We'll create different zones and it estimates SGD from each zone. And finally, we will use mode path to identify the recharge contributing areas and to track the flow paths. Then finally, to estimate the residence time of water in any specified place. Now the total SGD rate is going to be the sum of SGD rates from each model zone. The last chapter is estimating the nutrient flows from SGD. As you can see from the figure here, there are indicators of algal blooms expanding in the Great Barrier Reef, eutrophication effects, and different problems associated to nutrient flows. And as I said, our hypothesis is that SGD could be one of the contributing unaccounted sources of nutrients. To do that, we will just gather nutrient concentrations of the groundwater from the Queensland government groundwater database and from previous literature. Then we will upscale that by the nutrient concentration, this SGD, by nutrient concentration of the groundwater in member. And we will also use the historic nutrient data to project the nutrient concentration changes over time. And here is my timeline. I have collected enough data for my first and second chapters, and I'm still collecting data for the rest of the chapters. I am on time in presenting my confirmation. I already have submitted my final draft of the manuscript for the first chapter, and I'll probably make the progress report tomorrow. Then my second chapter, I already have compiled the data, the necessary data for the second chapter is just ready to kick off. And I hope the rest of the chapters will go smoothly. My special thanks to the university, our school, the Southern Cross Geoscience, my supervisors, my office mates for their support, and the university community at large. Thank you.